essentially entirely about birth, death, processes. I'm going to start by quickly doing a review of continuous time Markov chains from what I discussed on Tuesday, so that those of you who haven't had a chance to review your notes will have some background. Otherwise, the rest of the class is going to be impossible to understand. And after review, I'll go into the time evolution of a birth-death process. So we'll just look at the how a birth-death process works, and compute the stationary probability distribution. And this will fall essentially completely straight out of this, the continuous time Markov chain review. And then we look into a very important description of a birth-death process, which is the transition rate matrix. I'll show what the transition rate matrix looks like in the corresponding transition rate diagram. And then this will allow us time to figure, it gives us the background to go into a pure birth process, which is the first kind of real birth-death process. This is a process which has no deaths, it's only births. And we look into the stationary probability and the interarrival time of a Poisson process, and then finally into the general equilibrium solution for a birth-death process. So that's sort of the overview. At this point, the end of this lecture really is to get to the point where we can write down the solution to the general equilibrium of a birth-death process, and that is then directly used for a Markov chain or MM1 analysis, sorry. And really the next lecture is all going to be MM1. So all this really gets us to this point over here, and then this gives us essentially all the tools we need for analyzing MM1, MMK, MM infinity, and then to some extent MD1 and GG1, though we won't really study those very much. Okay, just to get the notation straight, I'm talking about continuous time Markov chains. And in continuous time chains, we are looking at the transition probability Pijt, which is the probability of going from I to j over an interval of duration t. So t is not the current time, t is the duration of this time. And so the idea is that if I make this interval longer and longer, or what is the dependency of the transition to go from I to j as a function of the duration, and this is defined as probability that x, the variable s plus t equals j conditional on xs equals I. Okay, so note that we have introduced a new variable s, and that variable s does not show up on the left-hand side. Okay, why can we do this? Why can we do this? Anybody have? I'm sorry? It's not really memoryless property, no. Homogeneous property, right. We talk about a homogeneous continuous time Markov chain. So because it's homogeneous, we don't really care what time it is. It's always the same. And so homogeneity gives us the fact that the s goes away. Okay, it has dependency only on t. So we define Pijt to be essentially a continuous random variable defined over the reals, which is giving us the probability of going from state I to state j, where we know that at time s we're at state I, xs equals I, and then we're saying given that this xs equals I is known, what's the probability I'm going to make this move to j, okay, at time s plus t. Now, since it's homogeneous, we can take this limit, which is qij, which is the kind of the rate at which you're going to move from one state to the other, and qij is defined as lim delta t tends to 0, pij delta t over delta t. Okay, so what we're doing is imagine that we are in some state I, and we have some other state j. In fact, we have a whole bunch of states j. Let's call this j1, j2, j3, just for the sake of argument. And from I, let us say we could go to 3 different states, right? So we are at some time s, we are over here. So xs equals I. So that is given. The trajectory is fixed at time s. Now what we're saying is, let's start moving time forward. We will compute the probability with which we enter states j1, j2, j3. Okay? And maybe it's the case that you're more likely to go to J1 and less likely to go to J2 in the beginning, but later on the roles change. it doesn't matter. We have some distribution over time of probability of going to J1 and J2 and J3. In the case of a memoryless distribution, okay, we have a constant rate at which we go to these J1, J2, J3. In an arbitrary the distribution, okay, we have different properties, but if it's a Markov chain and not an arbitrary stochastic process, then we're going to have this constant rate at which we're going to enter from J1, I to J1, I to J2, I to J3, and these constant rates are in fact even time independent because it's a homogeneous Markov chain. And so in some sense what we have is this delta t parameter which tells us in time delta t what's the probability, and what we can say is if I tell you delta t, then there is some rate which is Pij delta t, or maybe I should write this properly. This is Pij1 delta t is the probability of going from I to J1 in the time interval delta t. And Pij2 is the probability of going to state J2, and Pij3 is the delta t is the probability of going to J3 in time delta t. And of course I could stay in state I, which would be Pii delta t. Alright, so if I give you delta t, let's say delta t is 1 millisecond, then I can tell you in 1 millisecond what are the probabilities I'm going to stay in the state or go to these states J1, J2, J3. Okay, that is the interpretation of the term Pij t. Okay. Now Qij says, okay, let's take the limit as delta t tends to 0, and that gives us sort of the rate at which you leave the state. Okay, this is the rate at which you leave the state, and that is given by this limit over here. And so we define Qij. So this is only for Qij where j is not equal to I. And for j equal to I, we have this is basically limit delta t tends to 0, 1 minus Pii delta t over delta t. Okay, and there is we're doing it in a funny way like this, and the reason I'm not going to go into, just take it for what it's worth, but this is done so that delta sum over j Qij equals 0. Okay, we get that summation out of that. And then I'm basically just revising what we talked about last time fairly fast. And then the rate of change of probability, I pretty much gave you the result, again without any explanation of it. And we get this result which says a d pi j by dt, which is the rate of change of the probability. Yes?
According to your last class, Qii is like Pii delta t minus.
Oh gosh, what did I do over here? Yeah, that's right. It's a negative quantity, -1, sorry. I could have put a negative here. I forgot to do that. You're right. Yeah. Sorry. Otherwise, yeah, 1 minus. So Qi is a negative quantity. That's why you get the summation to 0. Sorry. Right. So I was going to say that the d pi j by dt, which is the rate at which so pi I is sort of the probability of being in time I, and state I at time t. So we get the rate at which this probability itself changes has been given by this one, Q, well, pi j, so Qjj, pi j t plus sigma k not equal to j, Q kj pi k t. And this looks a bit obscure, but the easiest way to understand it, and we will use this when you do the birth-death process in just a few minutes, what's going on really is that I can start looking at the rate at which probability flows into a state. And the rate at which probability flows into a state is the probability of being in that state, pi k, multiplied by the transition rate from k to j. Okay? And so we just sum up all these rates, and then this can be interpreted in this fashion of probabilities entering and leaving a state at a particular rate. And I drew that faucet last time to show you what was going on. Finally, the stationary distribution can be given by just setting d pi j t by dt equals 0. Okay, and if you just set it to 0, then in fact we will find the stationary probability distribution for a continuous time Markov chain. Okay, so life gets much easier when we look at a birth-death process, because in the birth-death process, instead of having the arbitrary, instead of going to any J1, J2, J3, Jn, but in fact we have an infinite number of states. We could have transition probabilities defined for any number of states. In a birth-death process, we can only go to state J minus 1 or J plus 1 from state J. So the number of things you need to define gets much simpler, and so we can start looking at the time evolution and the stationary probability distribution of a birth-death process quite easily. And to do this, I'm going to refresh you about this notation change. So here is a notation change. First, we'll define Q J plus 1, okay, to be the same as lambda J. Okay, so lambda J can be interpreted as the rate at which we go up. The population increases at a particular rate. Lambda J, it's the transition probability, this limit, of going from J to J plus 1. Okay, and we frequently draw this like this. We have a J, we have state J, we have state J plus 1, and we go to J from J plus 1 at the rate lambda J. All right. Similarly, we define Q J minus 1 to be equal to mu J, and so this is the rate at which we depart. So note that mu J is not from J plus 1 to J. Mu J is coming out of J. Okay, and this is it. And the third thing is we denote pi J equals Pj. Okay, this is a change in notation we're going to do, and we'll just use Pj from now on, but it's the same thing. Pi J is the probability of being in particular state J, and in the stationary sense, of course, Pj, we have Pj and Pjt. So Pjt is the time-dependent probability, and Pj is the stationary probability of being in a particular state. Okay. So given these change of notation, I can immediately write down this rate, this one over here, which is the time evolution of a birth-death process, and the stationary distribution of birth-death process, by basically plugging in these values over here. And this allows us to write down the time evolution we know that just with this change in notation and there, we just know that dpjt by dt equals essentially minus lambda j plus mu j pj t plus lambda j minus 1 Let me just write this down and explain what's going on. Okay, so what's going on over here actually is not particularly hard to see. We know that sigma j, I just erased that, I guess I didn't erase it, or maybe I did. Sigma j q jk, sigma j qij then equals 0. Okay. So what does this mean? Intuitively, we're saying the total amount of probability flow entering a state and leaving a state sums to 0. Okay. How do we get this? We get this because we are defining Q in terms of P's, and the P's are just telling you the transition probabilities, and at any moment in time, the probability of either leaving the state or staying in the state must sum up to 1. So sigma Pij, where you sum over all the j's, is going to be 1, because something is going to happen. Either the Markov chain stays in the same state or it goes to a different state. There's only two things that can happen. So if sigma Pij equals 1, then by defining Qij and Qii in this fashion, it has to be the case that sigma Qij equals 0. Okay, and that has the interpretation that I just said. The total sum of rates entering and leaving is going to be 0. If this is true, and we know that the only rates entering and leaving a state are lambda j and mu j, right? There's no other transition probabilities. We can't go to j plus 2 or j minus 2 or anything like that. It must be the case that qjj equals minus lambda j plus mu j. Okay, remember this is the total rate leaving state j, and of course from this figure it's obvious that the total rate leaving state j is lambda j plus mu j, right? We just get that just from observation. And similarly, when we take the summation sigma k naught equals j q kj pi k t, well, this pi k t is just p k t, and then the only two values for k naught equals j which are non-zero, the only two values are q j minus 1 j and q j plus 1 j. Okay, and then looking at this state, looking at these substitutions with the the values that come in are essentially lambda j minus 1. That's the rate at which you enter this state. So let me use a dashed line. So you come in at lambda j minus 1, and you enter from here as mu j plus 1, right? Those are the two arcs that are entering the state. So the total arcs entering the state are nothing more than mu j plus 1 and lambda j minus 1. And what we're saying over here is that mu j plus 1 p j plus 1 t, okay? So this is the rate at which you enter, and this is the probability of being in the j plus 1 in the first place. Similarly, you enter from j minus 1 with lambda j minus 1, and you're there with prob p j minus 1 t. And if you sum these two up and you subtract qjj, which is lambda j plus mu j p j t, that sums up to basically 0 in the stationary case, for the stationary distribution. Or if it doesn't sum to 0, that is the net rate at which the probability of being in state j changes, which otherwise that is dpj t by dt, right? So the rate of change of probability of being in a state is derived from the rate of the probabilities of being in the adjacent states pj minus 1 and pj plus 1 at that time t, and the rates of flow of these probabilities. So as soon as you make this mental leap of saying probabilities are like water, the amount of probabilities like water, and we have rate of flow of probabilities entering and leaving a state, then these equations become trivial. Okay, so something funny is going on. Okay, what's going on that's quote unquote funny is that we are deriving these equations purely from mathematical basis. There is nothing here which cannot be justified simply on the basis of random variables and families of random variables and so on, right? This is how I started, and you know, we have a perfectly valid line of reasoning based on mathematical formalism. There is nothing here that is hand wavy. Okay, this is very clean mathematical formalism. Yet it turns out that once you go through this process, you can draw this figure here, and after you draw this figure here, you can pretend that it's like water flowing into some vessel, okay, flowing into a state and leaving a state, and so you can at that point forget about the mathematical formalism. Okay, from the perspective of a practitioner, from the perspective of an engineer, or perspective of somebody who wants to use queuing theory rather than develop queuing theory, you can essentially forget about all this. So we did all this stuff just to make sure that we're not, you know, making a mistake. You know, we're not completely off the wall. But however, once we get this and we write this figure down, which is the state transition diagram, at this point we can forget about these limits, and they will come and bite us in about 5 minutes, because we need to make sure the limits actually exist, right? I just said that, and I have an assumption over here, assuming the limits exist, p delta t over delta t has to exist. Okay, we'll come to that in just a minute. But assuming that the convergence happens, which we'll talk about over here in convergence, we can set aside the basis and move on a different degree, a different abstraction, and this abstraction makes it much easier. Now, even though it makes it easier, it is a little bit confusing, because what we're talking about is the rate at which probability increases and decreases. Okay, and so what does it actually mean for a rate of that probability increases and decreases at a particular rate? I can keep talking about it, but you have to think about it. Okay, you have to really internalize the notion that the rate, that there is something called dpj by dt. Okay, what is the meaning of dpj by dt? I have some state j, let's say j is 5. So I have the state 5 at some time, let's say time is 20 seconds. So I have some probability of being in some state at time 20. And dpj dt by dt tells me the rate at which that probability of being in that state increases at that time. Okay, that is the slope, okay, at that point in time. Okay, and that is just telling you this is the way. So it can be more probable. So if the slope is positive, then at time 21 I could be more likely to be in state 20, for example. Okay, whatever state it is. So we are looking at the rate at which we can start making probabilities. Rate at which the probabilities of being in a particular state are changing over time. That's what these derivatives mean over here. Okay. So there is no way for me to kind of get it into your head. You really have to think about it. Try some numerical examples. Think about it. And when you do it, you kind of hopefully understand what dpj t by dt means. This is the time evolution of the state probability, what it means. Okay. Any questions about this so far? Yes. Oh, you don't have a question. Okay. It's dangerous to scratch your head in this class because I didn't have a question. Okay. So all this is basically, I'm just revising what we talked about. I'm just going to write down the last set of equations and we'll take a break. And the last equation really is nothing more than the stationary probability distribution, which is setting dpj t by dt to 0. What are we saying? In the stationary case, when everything is nice and everything has reached its final values, this rate of change of probability should be 0. Okay, nothing should change. If the probability of being in state 5 is 0.2, then it should stay at 0.2 no matter what, because it's stationary. That's the definition of stationary. So we get the equation. We just set the left-hand side to 0, and we get minus lambda j plus mu j plus lambda j minus 1 pj minus 1 plus mu j plus 1 pj plus 1 equals 0, j greater than or equal to 1. Now we have a corner case. That's obvious because in the 0th case we don't have anything coming in and we don't have anything going out, right? So we just get two terms, and those two terms are exactly minus lambda 0 p0 plus mu 1 p1 equals 0. Okay, so these two equations give you the stationary distribution of a general birth-death process. Okay, and as you can see, this is derived completely straightforward fashion from these two equations over here. Now, I didn't tell you how these came here. These are kind of, just gave these to you, but intuitively you can see that these are related to the discrete time Markov chain that we considered earlier, where we looked at the stationary probability distribution of a discrete time chain. We had this theorem. Again, I tell you where the theorem came from, but the stationary distribution in the discrete time chain is basically related, except that we now, went from the p's to the q's. Okay, we have to go from the probabilities to the transition rates. Okay. All right, so I expect some of you to be confused. So anybody who hasn't read the notes in the last day or two is probably going to be confused, and that's it's unavoidable. Sorry about that, but you have to keep up with this. Otherwise, it just gets more complicated over time. So, okay, so let's take a brief break here, and because that's the probability of being in your own state. Okay, so this is the probability multiplied by the rate of decrease in probability. Okay, and then this is the increase because you're leaving the state with lambda j plus mu j, and you're entering with lambda j minus 1 pj minus 1 and mu j plus 1 pj plus 1. Okay, we should probably continue here. Okay, so wanted to kind of make a few observations before we move on, just to kind of simplify these things. And first observation I'm going to make is that this equation over here, this equation and this equation over here are true for all continuous time Markov chains. Okay, it's not just for birth-death processes. All right, so the abstraction we have of having the rates coming in, multiplied by the probabilities which are used over here will be true for all continuous time Markov chains and not just birth-death processes. In other words, I can take any continuous time Markov chain drawn in this fashion, okay, where I can actually go to other places, not just here. For example, all right, let's say I have these states, I have another state over here. All right, so if you look at this state J, I can go here or here or here, okay, and then I leave in just one way, right? So I'm sorry, I enter in just one way. This is this one, okay, and I can leave in 1, 2, 3, 4 ways, okay. Even for this arbitrary thing, I can simply use the same idea. So if I were to number this, let's just call this 1, call this 2, 3, 4, 5, okay. So I can look at the rate Q23 as being the rate at which I'm leaving 2. So I can basically write down the following, what's called balance equation. I can say that how many ways can I enter? I can only enter one way, so it's Q32P3, okay, is the rate at coming into 2, okay, and then I'm going to say equals, okay, all the ways I can leave. Okay, here I can leave in just 2 ways. I can go up or I can go down. Here I can leave in multiple ways. It's going to be, so instead of taking the negative, I can just put equal to in between. I can just say Q21 P2 plus Q23 P2 plus Q24 P2 plus Q25 P2, for example. Okay, same balance equation idea holds true, and as you can see, it's, I don't need to go through all the math. I can just look at it and write down the balance equation for the state. I can write similar balance equations for all the different states as well. Okay, so just to give you the power of this approach over here, and I should also add that in any continuous time Markov chain, not only can you do this, but let's say you have some continuous time Markov chain, some arbitrary one. I can draw a cloud like this and isolate any number of states that I want. And similarly, I can write down the balance equations for entering and leaving the cloud. All the arcs, the cut set of this graph, which is the arcs which are leaving this cloud over here, I can write balance equations saying the total probability entering the cloud is going to be the total probability leaving the cloud in stationary's case. Okay? When it's not stationary, that total imbalance is the rate at which the overall probability of being in that cloud changes over time. Okay, again, this is you can just write this down without having to look at the underlying equations. And this, this is something that is not relevant in this course. But if you're going to use this, you can actually show that you'll actually use this for non-birth-death processes, which is something we don't actually consider in this course. Okay, so that's one observation. The second observation is that there is a way of representing. Let's just take both of these equations are essentially the same equation. Okay, I'm going to write it down in a slightly different way, and this is called the transition rate matrix. So this is the state transition rate diagram. Okay, it looks like the state transition diagram for discrete time chains, but it's not the same. Okay, it's not the same because the annotations on these arcs are the rates. Okay, and moreover, we don't have a self loop. We don't have to put the self because the self is nothing more than the sum of all the negative of the sum of all the other rates. Okay, we have this 1 minus p delta t minus 1. So if you know what the other rates are, we don't actually need to put that down. Anyway, we'll see what it looks like in just a minute. Okay, but all I wanted to point out that even though it looks like a state transition diagram, it's not. It's a state transition rate diagram. Okay, and so you'll be careful about that. The second thing I wanted to say is how do we write this down? So let's say we write the matrix like this. We say P0, P1, P2, whatever, and this is a sort of a infinite dimensional matrix. Okay, it's infinite in this dimension, and we can write down a separate infinite dimensional matrix. Actually, it's infinite in 2 dimensions, but that never bothered anybody. So here lambda 0, minus lambda 0, lambda 0, 0, and mu1, minus lambda 1 plus 1, lambda 1, okay. I should probably not draw it like this. Okay. Let's look at this matrix over here. Okay, I should say look at the product of these two matrices over here. This is just a row matrix, and that's a proper matrix. Can the people on that side even see this? Or okay, if you can't, this is equation 18. Okay, in the notes. So if you do the matrix multiplication, what you'll see is that you get P0 multiplied by minus lambda 0 and P1 multiplied by mu1, okay? And that's just this, minus lambda 0 P0 plus mu1 P1, that's equals 0 is the first equation. These equations are nothing more than the appropriate, column multiplied. For example, we get P0 times lambda 0 minus P1 times lambda 1 plus mu1, and so on, right? Plus P2 mu2, okay? So if you take this product of these two matrices, you in fact get exactly this or this, okay? So let's just call this one capital P. I'll draw that because I can't do bold, and we'll call this the Q. All right, so we get these two matrices, P and Q. P is just a vector of the state probabilities. Yes?
So the stationary points are the eigenvalues of Q?
Yes, exactly. But I don't want to use eigenvalues, so yes, in fact, that's what it's going to be. So we have the P matrix is nothing more than the state probabilities, okay? P we don't know. P we don't know. When we solve a Markov chain, what we're really doing is we're finding out what the P values are. We don't know what P's are. We know what Q is because that's the definition of the Markov chain. The Q's are these values over here. So when you write down the Markov chain or continuous time Markov chain, you're going to annotate it with the state transition rates. So you write those down. So you've got Q, and you want to find out P, okay? Let's just keep the notation going for just a second more, and you'll see what happens. So for the time evolution, all we have to say essentially is that dP t by dt, okay, equals PT Q. Okay, so what is PTQ? PTQ is just this. Okay, if this is annotated by by t's, this is of course not annotated by t's. Why? Because this is a homogeneous Markov chain. So we multiply these two together, so we can define P and similarly PT. What you're saying is that this equation, or this set of equations, is just this very simple matrix equation, dpt by dt is PTQ. Okay? And the stationary probability is just nothing more than PQ equals 0. Okay? So if we want to find out what P is, that's a stationary probability distribution, we just have to solve PQ equals 0. Okay? And if you do this, basically we get what P is, because that's what we're doing over here. If you want to find out the time evolution, we just do this. So it all boils down to writing down Q properly. Okay? So what we want to do is a technique that allows us to draw this graph and just write down the value of Q. If you can do that, you can give this to MATLAB. Say, here's my Q, tell me what P is, such that, PQ equals 0. Okay? And that makes your life easy. So what I'm going to do is to show you how to write down the Q matrix for a birth-death process. What you can do in your homework or something, just to make sure you understand, is to write down the Q matrix for arbitrary continuous time Markov chains. Okay? It's not very hard to do. So I'm going to erase this because I don't need that. But so what is P? Well, P is simple. It's already written over there. Let's focus on the Q. Okay. So I look at this Q matrix over here. I guess I don't need to do this. I'm just going to refer to that diagram, and I'm going to draw that again. Okay, so just look at a fragment of the chain over here. If you look at the diagonal matrix elements over here, the diagonal elements are nothing more than the, if you number it as starting from 0, okay, the diagonal elements are nothing more than minus lambda j plus mu j, right? So I can just, this is just a negative of the quantities that are leaving a particular state. So if I'm looking at j minus mu j plus lambda j, that's it. Okay? And if you look at the elements above, it's just lambda 0, lambda 1, lambda 2, lambda 3, and so on. What are these? These are just the values that you just read off the top. And what are the elements at the bottom row? Below the diagonal, these are just mu 1, mu 2, mu 3. Okay? So if you have a state transition rate matrix, a figure, you can actually just write it down by inspection. So let's do an example. Okay, let me do it over here. So I'm just going to draw a 4-state Markov chain. 0, 1, 2, 3. And I have this rate matrix here. 1, 5, 4. And then the other way I have 5, 8. Okay. So what's the state transition rate matrix? It's now, I can just write it down without really thinking about it. Okay. So the 0th element is what's leaving here. Well, that's minus 1. What's leaving state 1 is minus 10. What's leaving state 2 is 8 plus 4 minus 12. And what's leaving state 3 is minus 10. Okay, so we get the diagonals like that. And then above the diagonals, we just have to write down the values along the top, which is 1, 5, 4. Okay, and below the diagonals, we write down at the bottom 5, 8, and 10. So we get 5, 8, 10, and then the rest are zeros. 0. Okay, so this is the Q matrix for this state transition rate diagram. Okay, it's just very, very simple. Alternatively, you can just write down 1, 5, 4, 5, 8, 10, and then all you need to do is to make sure that the sum on each row is 0. Sum on each row is 0. You can verify that by just quickly looking at it, that it's sum on each row is 0. So this gives you the Q matrix, and then you can plug that into here, and at this point you can figure out what P is, okay, which is the steady state transition probability of being in each state of this particular Markov chain. So just to, well, I guess I haven't solved it here. But for example, if I want to tell you the probability of being in state, what's the time evolution probability of being in state 0, I can write that down from this matrix as, so d p0t by dt equals minus p0t plus 5 p1t. Well, what am I doing over here? I'm saying I'm leaving at minus 1, and I'm entering with plus 5 with p1. So it's minus 1 p0t plus 5 p1t. For this one, dp1t by dt is minus 10 p1t plus 1 p0t plus 8 p2t. Right? You can just write that down. And so you get a set of differential equations. You solve them, and that tells you the time evolution. For stationary probability distribution, just like we had the plug and chug approach, we have the same approach over here, and we can simply write down the equations for this, for PQ equals 0. I'm not going to do that, but you can figure it out. Okay, any questions about this so far? Okay, so yeah.
So
can we, instead of doing the stationary probability distribution, we can solve the general differential equation, and then we will have both the transition distribution probability and
correct. That's right. The limit will tell you the exactly. Yeah. That's not. In fact, I'm going to do that right now. Yeah. Any other questions? Yes.
In steady state, I think that equation is not enough to solve that. You should also have the summation over all elements of Q sum to
Yeah, we should. I mean, yes. I'm ignoring the normalization condition, but yes, we are going to do that. Yeah. Without that, it's not going to work. So basically, we need to have sigma j pj equals 1. So I'm just pointing out the importance of Q. This is trivial, so I left it out. But when we talk about Poisson, you'll see we actually need it. In fact, for general equilibrium, we need it. But I didn't want to emphasize that. Yeah. Any other questions? Okay, so let me set the stage for a pure birth process, and then we'll take a short break. I need to end the class a bit earlier today because I have to go for a meeting at 1. So we'll do the pure birth and then the general equilibrium. So I'm done with these things. Matrix. Okay, so we do the pure birth. I don't need the review. Okay. So one of the nice things about birth-death processes is that now you really understand what a Poisson process is all about. Okay, you guys, until now, and unless you studied queuing theory already, you don't know what a Poisson process is. Okay, now you will learn exactly what a Poisson process is in a way that you will never forget. Okay, because it's so easy. You only forget things that are hard. This is so easy. There's no way you can forget it. What's a Poisson process? Poisson process is a birth-death process that doesn't have deaths. That's it. So all these negative rates are 0. And what's more, all the upper rates are the same, lambda. In fact, the probability of going from any state to any other state is lambda. Okay, any state to the next higher state is lambda. So we don't have lambda 1, lambda 2, and all this stuff. It's just lambda all the way. All right. So we can draw this, and now we can start thinking about what does it mean, and how do we compute the stationary probability distribution and other stuff like that. So, well, I'll talk about what it means, and then after the break, I guess I'll tell you what we to compute some numbers about it. Okay. So. Okay, I don't need this stuff here. All right, so what does it mean? Let's go back to the motivation for a birth-death process. The motivation for a birth-death process is a population, all right? A population of individuals, and we can now think about this in population as having everybody lives forever, okay? It's infinitely growing population, so that's one thing. This is an unstable process. Okay, a Poisson process, from the perspective of queuing theory, is unstable. The queue grows, or the population grows without bound. Okay, so that's the first thing. The second thing is that because we have zeros all the way, all states are basically the same state. We don't have any dependence on state. Okay, so if I have a population of size 2,000, the rate at which arrivals come in at 2,000 is the same as when the rates came in when I had 20 or 5. Okay. Think about that for a minute, okay? Let's say that I look at the arrivals into the classroom over here, all right? So if it's 11:25, there are 1 or 2 people, all right? At 11:29, there's more people coming in, and at 11:35, nobody is coming in, all right? The rate at which arrivals happen is dependent on the number of people in the class. The overall population of students in this classroom is finite. Because it's finite, what happens is there is a natural decline in the arrival rates. Okay, these lambdas represent arrival rates. Okay, we introduced lambdas from the notion of probability, but we can equally well think of them as arrival rates of events. Okay, it turns out to be isomorphic. So we actually are seeing a situation that is not Poisson. Okay, when you have population is small, few people in the classroom, you have a large probability of going to the next state. But when the population is large, and of course when it reaches the full size, everybody is going to show up for today, is here, lambda is 0, right? So it is a birth-death process, because people are coming in ones and twos and so on, or one at a time actually, to be more precise. And presumably people are leaving. In each break, 1 or 2 people sneak out. So there's some deaths going on over here. But it's state dependent. The rates are state dependent. Poisson says, no, it's not state dependent, it's state independent. No matter the population size, I have a constant rate lambda of a new, of somebody being born, right? So this is a pretty funny assumption. Okay, it's a pretty funny assumption going on over here. And this independence of the arrival rate from the state is what makes Poisson both powerful and, in many cases, incorrect. Okay, so I could model the arrival of people into this classroom as Poisson. I would be wrong, but it will give me some idea what's going on. So this is both the curse and the blessing of queuing theory. Okay? The curse is that I have to make obviously wrong assumptions, and the blessing is if I make those obviously wrong assumptions, I get something which is sort of kind of nice. Okay, when we start looking at MM1 queues, you'll see that Poisson shows up all over the place. We have expecting Poisson arrivals, Poisson departures, etc. But I want you to get this intuitive understanding of Poisson. Poisson is just essentially like a geometric series all over again. Geometric series says I'm doing Bernoulli trials, I'm doing IID trials, and at each point in time I'm doing a trial, and that trial is independent of everything that happened before. I have no memory. Poisson says at any point in time I have a constant rate at which new people are arriving, lambda, of going to the next state. Once I get to the state, I don't really care how many people are there. I don't care what J is. It could be 10 or 20 or 10 million. The rate remains the same. So that's why I wanted to give you the intuitive understanding of Poisson, okay? Because you see over and over again in networking, you see it in other places, we assume arrivals of Poisson. You have to think, is it really Poisson? Is it really the case that independent of the population size, the arrival rate is the same? Chances are pretty good it's not the case. Okay, this is only true essentially when the overall population is infinite. So you're not draining away the rate by arrivals coming in. Let me give you another example, and then probably I'll take a break. Imagine that you are in a small town. Okay, in a small town, this is a population of 115,000. Okay, which is I guess Waterloo, or let's make it smaller just to keep it simple. Let's say a small town of population 100. Okay, we have a telephone switch over there. Okay, telephone switch, and people are making calls. So the first person makes a call, and the second person makes a call, and third person makes a call, etc. And the calls are going on. Now one can start thinking, what is the arrival rate of calls, right? There's inter call time, right? First call comes in at 1 second, the next call comes in at 10 seconds, next call comes in second. Look at the inter time, and you can take the inverse of that as the arrival rate, right? It's a very natural definition. If I get first call at time 0, second call at time 10, third call at time 20, then I can say I'm getting calls at the rate of 1 call every 10 seconds. 1 over 10 is basically my arrival rate. It's 10 inverse. And that's a very natural definition of arrival rate. Okay, so when the population is 100 people and we have 1 call and the arrival rate is 1 in 10 seconds, I can expect the next call will come at time 10 and the third call will come at time 20. What happens when we get to 50 people? Okay, assuming they will only call each other. Okay, when you get to 50 people, they're all talking to each other. There's nobody left. There's nobody left. The arrival rate has got to go down to 0, right? So if you model this system as a Poisson arrival process, you're okay when you have 1 or 2 or 3 calls. Okay, you can say, well, what's called lightly loaded condition, it's okay. But when you get to heavy load, a lot of people are coming in, the Poisson assumption fails completely flat. Okay, so now you start thinking in terms of what's called teletraffic regimes. What is the regime under which Poisson works? Poisson works when the population size is infinite, okay, compared to the population of inside the queue, inside the queuing system, right? Because in this case, arrival rates are essentially independent of what's going on. Okay, we can decouple these things. But as the number of calls go in, then we essentially get into these non-Poisson type systems, mainly because you run out of customers, there's nobody else to serve. Okay, there's no more arrivals being possible. You'll see that you could just pay a little thought, you can see this is essentially the same as what I said about people entering this classroom. When everybody is here, there's no more people to come in, right? Then obviously there's no arrival rate. Arrival rate is going to be 0. So lambda is, I don't have a constant arrival rate. But for the small population sizes, I can say, yeah, for the first 5, 6 people coming in, it's approximately modeled by Poisson. So there is a value to it, but you have to be very, very careful that when you apply this, you're in the lightly loaded regime and not in the heavy load regime. Because in heavy load regime, the Poisson arrival assumption is not going to work. Okay? So all of this can be derived by just one figure, like this. Okay? That's the beauty of queuing theory, right? I can just draw this one picture, and everything I told you, you can just get it just from looking at this one picture over here. There's nothing I've said that's not obvious from just looking at this one picture over here. Just you have to think about it. There's nothing more to do. Just think about it, and you'll get all of this for free. Okay? Especially if I set this to be 0, then you're all set. Okay. Any questions about this over here? Yes.
I do see a system where the arrival rate can be modeled by Poisson, but what about the other way? The exit rate is 0. And is there a realistic system in which such a...
Exit rate is 0. The death rate is 0. Death rate is 0 over here.
Yeah, but is there a realistic system in which such a...
Okay, so the question is, do we have pure birth systems, right? And the answer is yes, if you look at it the right way. Okay, we are if you don't look at it as a population, but we look at the number of events that have happened since time 0. Okay, I'm just doing event counts. Okay, so for example, I can ask you the following question: you're standing on this ring road and you're looking at cars going by. Okay, I want to ask you the question: how many cars have gone by since you started counting as a function of time? Right? If we assume that the population of this, here we don't really have a population per se, but if you assume that there is this arrival rate of cars which is essentially time independent, then it will turn out that the number of cars that you've seen, okay, and you do this every day, ask you after 1 hour how many people you see, that will exactly follow a Poisson distribution. And I'll prove it. After the break, I'll prove it to you. But here we don't actually have any departures, right? It's just arrivals. But we can model that exactly as a Poisson process because of the following thing. You can view this as a 0th car, first car, second car, and the number of cars you've seen does not change the probability of a new car being seen in the next delta t seconds, the next epsilon seconds, number of cars is, and so there is a way to axiomatically derive Poisson process from this assumption that in any time interval delta t, the probability of seeing a car is lambda delta t, and second, the probability of 2 arrivals in a small time delta t is 0. Okay, probability of 1 arrival is lambda delta t, probability of 2 is 0. If you just give me these 2 assumptions, I can actually derive the Poisson equation for you backwards. But it's easy to do. I can find it in any textbook. It's not a big deal. Okay, but I want you to have a different perspective because that is the axiomatic approach. There's no intuition there. Okay, this is a intuitive approach based on populations. I think it's a more intuitive understanding of what's going on. Any other questions over here? So I hope everybody understands what a Poisson process is now. Okay, everybody get it? Okay, it's a pure birth process, no deaths, and the births can be corresponding to arrivals. Okay, so now that we have this process, we can now start doing some fun stuff with it. And let me take a short break, and then we'll do some we'll do some nice math, simple math, when it's there. So we're going to study a pure birth process, and we're going to essentially look at two parameters of interest, the stationary probability and the inter-arrival time distribution. So let's do the stationary probability for this. So I erased that, but I can just write down the following. Let me just write down the Q matrix. The Q matrix is, well, what is it? Well, what's the rate of leaving state lambda? It's always lambda. And the probability of entering is always going to be plus lambda. So we get lambda here. Sorry, am I doing this right? Yeah. And then I come down with 0. So it's a pretty straightforward matrix. Okay, there's not a whole lot going on. And so we can write down dp0 t by dt, the time evolution, as minus lambda p0 t. Okay. Right. Am I doing this right? I think I made a mistake here. Because of the zeroth state, let's see. Yeah, it's a 0 coming in. That's right. Yeah. So this is the column over here. Minus lambda 0, so we get dp0 t by dt is minus lambda p0 t, right? And so this looks just like this. dx by dt equals minus lambda x. All right? So what is xt? E to the minus lambda x. Okay? Or in other words, you can just say P0 equals e to the minus lambda t. All right? That's basically what we get over here. Now, we're saying that over here dp, so the other equation we have is that dp1 t by dt equals minus lambda, let me say over here, okay, minus lambda p1 t plus lambda p0 t. Okay, so why is this? Well, I'm leaving with minus lambda to the upper state over here from 1, and I'm coming in with from p0 with rate p lambda. So I just get this equation by inspection, and then I can set this to be minus lambda p1t plus lambda e to the minus lambda t. Okay, and this is a very simple differential equation, and if you just kind of do the integration, you get p1 equals e to the minus lambda t. Lambda e to the minus lambda t. Okay, so if you differentiate by parts, you see right away that you get this, right? If you differentiate this by parts. So we know what p0t is, we know what p1t is. If you do p2t, okay, same thing. dp2t by dt equals minus lambda p2t plus lambda p1t. Okay, and now I can substitute p1t over here as lambda e to the minus lambda t. I get basically lambda square e to the minus lambda t. And if you integrate this, you will find, okay, if you do it basically j steps, you find pjt is nothing more than lambda t to the j by j factorial e to the minus lambda t. Again, this is just a very simple exercise in backward substitution, at each step, because I'm just solving p0t, putting p0 into p1, p1 into p2, and so on, which I get from this matrix over here. And so I have got the time evolution of each state right here. This is exactly what I was saying earlier, right? I got a time evolution in each state. So what does it mean? It means the probability of having a population of size j at time t is this, okay? And this is nothing but Poisson distribution with parameter lambda t. When we studied the Poisson distribution about a month ago, I said it's e to the minus lambda, lambda to the j by j factorial. Okay, it's just lambda t over here, and so lambda, so it's Poisson distribution parameter lambda t, okay? Which means that the expected value of this, expected value, well, of, I don't know, pt, pjt, is going to be nothing more than lambda t. Actually, I should say pjt, I'll just write down expected value. Okay. In other words, in time t, I'm expecting to have lambda t arrivals. Okay, because that's the mean of this distribution over here, or the expected value of this distribution over here, and which makes sense, right? What does it say? It says that if t seconds have passed, and I have a arrival rate of lambda, then I should see on average lambda t arrivals. Okay, so this solution therefore tells us why it's called Poisson distribution, okay, or Poisson process. The Poisson process can be defined as a process in which the number of arrivals in any time t is the distribution of the number of arrivals in any time t is given by the Poisson distribution with parameter lambda t. Okay, so these are equivalent. These are completely equivalent to say this is a birth test process or a pure birth process at rate lambda, and it is a process which has pjt given by this equation over here. Yes? Is there a stationary distribution for the? Yeah, we can find. I mean, the stationary distribution over here. It's actually not going to be stationary. Okay, why is it not going to be stationary? Anybody want to tell me that? It's not recurrent, right? All states are transient, right? Because you enter a state and whoop, you're out of the state again. So you never come back. When you don't have this, there's no stationary distribution. So for Poisson process, in this fashion, we don't really care about stationary per se. Yes?
But from the Q matrix, the eigenvalues are on the left-hand side. It should be stationary. Okay, so you will find, if you try computing the eigenvalue, you will find that it's going to be not working out. But it's a diagonal matrix. The eigenvalues are the elements on the diagonal.
Right. Yeah.
So they are all minus.
They're all minus.
So they are on the left-hand side.
It's not applicable to this case.
Yeah. It's. I mean, the thing is, we don't. I mean, the thing is. Okay. Let me answer that slightly differently. We can use the theorem. We can use the theorem about stationarity and the PQ equals 0 when conditions apply, when assumptions apply. What is the assumption? Ergodicity, right? It has to be recurrent. This is not a recurrent.
Actually, even putting the theory behind this Markov chain process behind, actually, this differential equation has an equilibrium point. And from the eigenvalues, it should have an equilibrium point.
The thing is, I'm saying if it's ergodic, then it's stationary, and this is how you find it, right? Then you're saying, okay, forget about ergodicity, this is the station. It is meaningless.
No, I mean this differential equation.
Is
it dependable on ergodicity?
Yes. Without the ergodicity, without ergodicity, the stationary value, the stationary probability distribution has no meaning without ergodicity. Okay, the matrix is infinite, but that's fine. I mean, I'm just saying, without ergodicity, even you can't even apply the PQ equals 0. Okay, so the conditions under which PQ equals 0 are valid are not being held. So you can't say, okay, well, it has eigenvalues. Fine, it has eigenvalues. Doesn't matter. Okay. Because it's not relevant. It's not relevant. The conditions don't hold. So the point I want to make here is that the Poisson process doesn't have stationary probability distribution because all states are transient. Okay, there are no recurrent states. All states are transient, and if it's not recurrent, then all the theory goes out the door. Yes.
If you don't try to solve for the eigenvector as he's suggesting, what will happen is that you'll get the zero vector. You'll get 0, 0, 0, 0, and that's not proper distribution.
Right. So but I don't want you to even try doing it, okay? Because that would be wrong to begin with. Okay. So that's why for the Poisson process we are not solving for stationary because there is no stationary probability distribution. We only have this. So that's. So why am I saying stationary over here? I didn't mean to say that at all. I was going to say time. What are you going to call it? Let me just call this PJT. There. Okay, so second thing I want to look at is the inter-arrival time, or the expectation of the inter-arrival time. So what I'm looking at is like this. Let's say I'm at state 2, and now there's going to be some time before 3 arrives. Okay, and by the way, it's the same exact thing whether 2 arrives in 1. When at 1 you come to 2, or 2 you go to 3, 3 go to 4. The inter-arrival time process is the same. Okay, because we are state independent, right? So what we want to do is to compute the inter-arrival time, and we can, let me write down exactly what we're talking about here. So let me draw it over here. Okay, I should keep this fast. So let A equals time between two arrivals. Okay, that's just a random variable. Time between two arrivals, and as you can see, A takes some distribution. So we want to compute the cumulative. Let's start with the cumulative for A. Again, why you want to compute the cumulative for A? Because, as I said earlier, for continuous time functions, it's better to work with cumulatives rather than density functions. It's always best to compute the cumulative, differentiate it, and get the derivative, get the density rather than the other way around. So we'll use that trick. Let's find the cumulative for A, which basically is probability that A is less than some value t, okay, or less than equal to, which is nothing more than 1 minus p A is greater than t. Okay. Now, what is we saying p A greater than t? We're saying that the interarrival time is greater than some value t. Okay. But this is exactly saying that there have been zero arrivals in time t. Okay. It's exactly saying the zero arrivals in time t, which is nothing more than 1 minus p0 t. Okay. Because if nobody arrived in time t, there will be zero arrivals. That means I'm staying in state 0 of my birth process. All right? And so we know that that's nothing more than 1 minus e to the minus lambda t. So that gives me the cumulative density function of A, which means that the density function for A is nothing more than lambda e to the minus lambda t. Right? And so this is an exponential distribution. What are we saying? If we have a Poisson process or a pure birth process, the interarrival time, the time that you have to wait between arrivals, which is just this one over here, is distributed exponentially. Okay, and this is sort of a fundamental theorem or a fundamental result. It's, as you see, it's a pretty straightforward result to prove. And it characterizes the Poisson process. Again, it can be shown that if interarrivals are exponentially distributed, then the process is Poisson. We have essentially a if and only if relationship between these two things. Okay, so that's nice. I can say it's a Poisson process. I can immediately tell you that the parameter lambda over here, lambda t, is a Poisson parameter, and that lambda over here also tells me the interarrival time distribution for this, and it's exponentially distributed. All right. What does it mean? If you just look at it, basically as t increases, the probability goes down exponentially fast. So keeping lambda fixed, as t increases, we're going to have a very rapid fall off. And if you did the homework assignment for chapter 2, you'll know that this is way faster than a power law. It's many orders of magnitude faster than power law. So we go down very fast, which means that things are going to happen fairly soon. Okay. In other words, on the time scale of lambda is when you expect to see transitions. Things go down very fast after that. Probability goes down very fast after that. Okay. Any questions about this? Okay. So let me. So that's pretty much all I wanted to say about Poisson. There are many things about Poisson distributions, and it shows up in all sorts of places, in statistics, in biology, and so on and so forth. But I just wanted to show you two simple demonstrations of what you can do with Poisson and the intuition. I'm going to move on now to the to the general equilibrium solution for a birth-death process. Okay, so how are we going to do this? Well, we're going to assume. What are we going to? Okay, let me show you. We started the birth-death process like this. Again, the same thing. Okay, so for the moment, let's assume that this is going to be ergodic. Okay, I'm going to assume ergodicity, and therefore it even makes sense to do the stationary distribution. So it cannot be a Poisson process. Okay, it's not at all. We have, in fact, positive recurrence. In fact, all states are positive non-null. So I can assume ergodicity. Of course, irreducibility is obvious, given the structure of the chain. So what I can do is this. I should probably go back to, okay, let me just write down the equation over here earlier. So I said for the stationary distribution, 0 equals minus lambda 1 plus mu 1. Actually, I take it back. Let me just do the lower equation. It said 0 equals minus lambda 0 p0 plus mu 1 p1. I should have left it up over there. Well, I can just say p1 mu 1 equals lambda 0 p0, or I can say p1 equals lambda 0 by mu 1 p0, right? Again, you can see this simply by looking at the equation over here. This is lambda 0, this is mu 1. So mu 1 p0 equals lambda 0 p0. So mu 1 p1 equals lambda 0 p0. I can just read it off from there. I just wrote it down over here. I wrote p1 equals lambda 0 by mu 1 p0. Now, by symmetricity, just from symmetricity, because all states are symmetric, I can write down immediately that p2 equals lambda 1 by mu 2 p1, right? I just kind of move 0 to 1, 1 to 2, okay, and 0 to 1 over here, so I get p2 this, right? And then p3 equals whatever, right? And so in general, I can write down the general value of this easily, that pj equals what? Lambda 0, lambda 1, lambda 2, lambda j minus 1 over mu 1, mu 2, mu j times p0, right? I'm just unrolling this. Okay, it's just simple. Okay, and I can write this simply as p0, the product. So it's a sort of pi, the product, I equals 0 to j minus 1, lambda I by mu I plus 1. Note that it's I plus 1 because, we have lambda over mu 1, right? It's not mu 0, it's mu 1. And so if I know P0, and if the Markov chain is ergodic, right? So stationary distribution exists, I can tell you Pj, the stationary probability Pj, simply from this. And how do I find P0? This is where I have to invoke the fact that sigma j, Pj equals 1. If that is true, then it must be the case that P0 equals what? We're going to take 1 over 1 plus, let me just write this down first and then you'll see what it is. J equals 1 to infinity, pi I equals 0 to j minus 1, lambda I by mu I plus 1. Okay. This one and all right. So what did I do over here? I said sum of all the pj's equals 1 because it has to be the case that the sum of all the probability of being in any state is 1, right? Got to be in some state. So we just put this as p0 plus p1 plus p2 plus p3 etc. onto p infinity equals 1, and so that's what I did over here. P0 plus these ones over here, just P0 multiplied by this product over here, which is this term over here. So I just took each of those. I've got to sum them. I'm going to sum them using this summation over here, right? Because all of these are the form P0 times this product, P0 times some other product for different values of j. And so I just sum it up and I get P0 is this. Okay? At this point I'm done because I know what P0 is. Okay? P0 is expressed in terms of what? Lambda I and mu I, which you can read off from the diagram. Okay? When you have a birth-death process, you can just read off these values. And if you can do that, then you can substitute back away to get all the pj's. So if you have a birth-death process and you can annotate the arcs, then you can simply use these two equations, this one here and this 2 here, and at this point you can just sort of plug and chug and get everything that you want. All right? And I'm going to, I earlier drew a 4-state Markov process. It's figure 6 in the notes. And if you look at example 19 in the notes, what I've done is I've used exactly this to compute the steady-state probability distribution of being in each of the 4 states of that 4-state birth-death process. And I would encourage you to actually, walk through, at least read through the example carefully, because that will tell you how it's done. Okay. So let me stop here, and then what I'm going to do next time is to use these 2 equations to compute all the parameters of interest for MM1. So it's the first queuing system. So we've spent 4 lectures just to get to the stage of being able to understand a very, very simple queue. Okay, it's all the background you need just to understand the simplest possible queue called the MM1 queue, and we'll study that next week, on Tuesday. Okay, thank you.